Hello, in this video I'm going to speak about the design of concrete beams. We created the 3D model to show the different members and designation of every member in a concrete structure. If you look at member number 4, it should be a slab on grade. Like this slab should be supported on the soil. However, we removed some of the soil to show the members underneath it. So you have here the number 4 as a slab on grade, number 5 is a floor slab, and this floor slab is supported on these concrete beams underneath that. And if you go to the upper level through the columns, you can have the floor or the roof, and this roof is supported on small beams next to each other. We call them floor joists, and the Canadian code specifies the distance between the floor joists to be not more than 800 millimeter, and they have a specific designation or a specific design for that. These joists normally are supported on girders or beams at the end, as you can see. Our point now is how to design a concrete beam to support the floor slab, and when we speak about the floor slab, the load on the beam can create bending moment, and also it can create shear force. We will start only right now with the bending moment or flexure. To understand the behavior of a beam under flexure, we have this shape. If you have a small member like that and you are applying bending moment, you try to bend the member in this shape. And if you go to a 3D or a bigger shape like that, and we apply the moment to the ends, and here at an elevation you can see the line AB. The line AB is the neutral axis, and the neutral axis means that it doesn't have any changes or any stresses. Its length will stay the same. But if you go to the top fiber here at the top, you realize that based on the radius and the curvature, this length here is less than the length of the member CD. However, the member AB didn't change, because AB now with our assumption is the neutral axis. Now we have three levels of the beam. The top level or the top fiber, which will be under compression in this case, and the intermediate, and not in the middle, I mean intermediate, like between the top and the lower phase, which will be AB, and that is the location of the neutral axis of the member. It doesn't have any changes. And then the other fiber or the other level is at CD, and CD, you can imagine that it has more extension based on this radius. When we are talking about extension, that means it is under tensile force. So I have compression force at the top and tensile force at the lower face of the beam. Now if I'm designing a reinforced concrete beam to resist this bending moment, we use that normally in a steel structure. We design that based on the allowable stresses, or sigma, equal to the moment, the factor moment divided by S, where S is the section modulus. And when we know the bending moment and we know the stresses on the maximum stresses of the material what we choose, normally Fy equals 350, and we multiply that by 0.9 as a factor of safety for the material, then I can get the S for the cross section. Now when I know my S, my section modulus, I can go to the design tables and choose a member which will fit within my space, and it satisfies the criteria for my building. So that can be a W section or I section or HSS channel, whatever. But the question is, can I use the same concept for the design of the concrete beam? The answer is no. Why is that? Because this member now combines steel and concrete. The steel structure only, or structural steel, has only one material, so I can use the section modulus and I can design it. But when I have reinforced concrete, I have two materials working together, that's the steel and concrete. And we have to assume that the steel and concrete have a full bond. So whatever happens at the same level for the concrete, it will happen to the steel. So the bond is very important to achieve a composite member. Now what will be the cross-section behavior of this combination of the concrete and steel? we start having one condition of the section, which will be the uncracked section. If I look at the cross section here, AA, and I have here the width of the beam is B, and I have a height of H, and we have here 3 bars in the cross section, and the regular shape of the section will be like this. And when this section is subjected to bending moment, the section changes to be inclined like that. And here you can have a compression force at the top, and the neutral axis there is no stresses, and here at the lower face I start to have tensile force. When we speak about uncracked sections, that means the stresses in the lower part of the beam, which will be tensile stresses, are less than the tensile strength of the concrete, so there is no cracks. The moment when the tensile stresses on the section is bigger than the tensile strength of the concrete, the section starts to crack. And this cracked section, you can see here, the concrete is cracked and it cannot carry any tensile force. So the difference between the two shapes here is, one is I have here uncracked section and the concrete is acting with the steel to resist the tensile force, because the tensile stresses on the cross section is less than the tensile strength. In this section, the tensile stresses is exceeded the tensile strength of the concrete. That's why the concrete started to crack, and we don't consider any tensile strength of the concrete, and the tensile force will be resisted by the steel only. So at the top here I will have compressive force and from the concrete, and at the lower I will have tensile force by the steel. So I have FC and I have FY. If I can calculate the forces FC as a compressive force at the top part, and I can calculate the force in the steel, now I can calculate the resistance of the beam for the bending, which will be equal to this force times the lever arm, or the distance between the forces. We will go through the details how to calculate the forces in the concrete and the steel right now. So as you can see, I have two members or two materials which are resisting the bending moment: concrete under compressive stresses at the top, and steel under tensile stresses at the bottom. Now when we speak about failure, what type of failure can we expect? We can expect that the concrete can fail, and that can happen when the stresses on the concrete is much bigger than the resistance of the concrete, or we can expect that the steel can fail, and that means the tensile stresses is much bigger than the tensile resistance of the steel. So every one of them has some benefits or some description. So the concrete here, if we have a concrete failure, the bad side of that is the concrete failure is really brittle and it doesn't work, and the concrete when explodes when it fails. So if I have concrete failure, that means we don't have any warning, we don't have any cracks, we cannot repair our building. So we don't want that. The steel failure, before it happens, it starts to elongate because the steel is more ductile, and before reaching the fracture of the steel bars, the steel will have elongation, and this elongation will be translated into cracks of the section. So we can see cracks in the beam, and that tells us, you know what, there is something here has to be checked, and then we can repair the beam. So when we design our members, we go from, or we design it to make sure that if any cracks or any failures will happen, it should happen with a steel failure. So we put it as under reinforced section. That's the terminology what we use in Canada, under reinforced section, which means that if any case of failure, we have to allow the steel to fail and not the concrete. Now, what does it mean to have to design reinforced concrete beams? We need to get the beam dimension. I want to see what is the width of the beam and the depth of the beam, because we create the formwork for that, and then we start to put the materials. What type of materials? I have to look at the concrete strength. I will specify the strength of concrete, F prime C. This F prime C can be 25 Newton per millimeter square, which is the strength of the concrete cylinder after 28 days. Or it can be 30, it can be 35, 40, and so on. So we have to specify the concrete strength, and we have to calculate the total area of the steel bars. So designing a concrete beam to resist bending moment will require three items: beam dimensions, choice of the beam dimensions, and we have to consider that these beam dimensions will affect the clear height within the building. We have to check with the architect and the architectural drawing, and we have to check also the deflection, which is a completely different topic. And we have to specify the concrete strength, what type of the concrete we are going to put in the form of the beam, and we have to put how many bars should we add to this beam dimensions. Now, to make sure that the concrete and steel are working together, we have few assumptions. These assumptions are: we have to consider a full bond between the concrete and steel. We have to say that, or assume that, the cross section remains plane, and we have to ignore the tensile strength of the concrete. What does it mean? If we go to this picture, if I have this cross section again with 3 bars, now I have to assume that the bond between the steel bars and the concrete is full bond. What happens here at this phase will replace or will match the whole section. So I have a full bond between the steel and the concrete. There is no relative movement for the steel inside the concrete. Number 2, the cross section remains plane. That means the stresses here, or the strain in this member, is equal to the strain in this member is equal to the strain in this member, because I have the cross section remains plane, and we ignore the tensile strength of the concrete. So the tensile force will be only resisted by the steel force. Now, to calculate the forces, as I mentioned before, I have 2 types of forces: the force in the concrete and the force in the steel. How I can calculate the force in the concrete? So now, if you look at the stress strain diagram of the concrete, it looks like in this shape, and here is the maximum F prime C. But we know that when we pour the concrete in a formwork, we have different conditions on the site. So it's the weather, it's a compaction, and the vibration. So many items can affect the strength, the final strength of the concrete. So we might ask for F prime C equal to 35. But what we can get on the site in the formwork might change, might be less than that. To account for this variance, for the workmanship and the delivery of the concrete, we count for material safety. So the material safety here is phi C, and for the concrete is 0.65. So we reduce the F prime C from here, and we use this value in our design as phi C times F prime C, and phi C equal to 0.65. Now, if you look at the cross section here, and we put this stress strain diagram on this section, and I have the neutral axis in this case, so the depth of the compression zone is this C, and the width is the width of the beam. Now, if I can multiply this area C times B, this area, and multiply this area by the stress time area, gives me the force. So the issue what we have here is the stress on the concrete is not linear. So it's very tedious to calculate the stresses here. So that's why the Canadian code and many other, like Euro code and the American codes, they introduced the stress block, equivalent stress block. What does it mean? It means that instead of having this diagram in this shape, I will have a stress block with equal distribution of the forces. In return, like the force here or the stresses is not phi c times f prime c, we introduce another factor which is alpha 1 phi c times f prime c. This phi 1 is a factor which can used to translate this distribution into a uniform distribution. What is the value of phi 1 or alpha 1? The value of alpha 1 is 0.85 minus 0.0015 f prime c, and it should be bigger than or equal 0.67. If you are using material or f prime c from 25 or 30, alpha 1 will almost be 0.8. So we can use alpha 1 for f prime c up to 35 Newton per millimeter square. So alpha 1 can be 0.8. So if you multiply alpha 1 0.8, phi c is 0.65 times f prime c, which you can choose from your supplier or based on your design. So I know this parameter here. Now what is the depth of the stress block? If you can see here, the depth of the stresses was c. Now to get the equivalent force here, which will have the CR equal to CR, we reduce the depth from C to be A. This one is A. So how we do that? We introduce a factor called beta 1. This factor beta 1, when I multiply it by C, so I can get the depth of the compression zone in the equivalent stress block. Okay, so beta 1 equals to, from this equation, is 0.97 minus 0.0025 f prime c. Most of the time for normal concrete with less than 35 Newton per millimeter square, so you can use beta 1.9. Now let's go back to calculating the CR. CR will equal to this area, which will be A times B. A times B, I have this area, and now I have to multiply it by this stresses. So these stresses are f prime c times phi c times alpha 1. Now I can calculate CR, and CR is the compressive force in the concrete. Now what is the second step is to calculate the Fs. To calculate the force in the steel, we have to create a balanced force, which means that the compression in the concrete will equal to the tension in the tension force in the steel. So to calculate the Fs, here I have to use the tensile force equal phi s times Fy, which is the yield strength of the steel, and times the area steel. Now the phi c is the material factor which considers the variance of the stress or the strength of the steel during the manufacture process. Because the steel is very accurate in the production, phi s equals to 0.85. And if you remember that for the structural steel, where we have a W section or HSS, we have 0.9. So I have 0.9 for structural steel, I have 0.85 for reinforcing steel, and I have, or reinforcing bars, and I have Fy. In steel bars, we use the Fy most of the time 400 Newton per millimeter square. In structural steel, we use 350 or 300. It depends on your material and what you choose. Now I can have the TR, which is here, and I can have CR. Now if I know CR and I know T, they are in balance, and I know their values from these two equations. If I know the distance between them, then I can calculate the resisting moment, which will be the force times this distance, or this force times this distance, or if I'm talking about the neutral axis, I can have this force times this distance plus the TR times this distance. So to make it easy, we use one of this force times this distance, and we can calculate the resisting moment. So the moment in this case will be TR times D is the depth here minus A half, because the center of the compressive force will be at half of the distance for the stress block, which is A. So I need to get beta 1 and times C, so I can get A. When I have my A, so the CR will be in the middle of A, and I have TR. Now D minus A half, that will be this distance, so T times D minus A half, then I can have the resisting moment of the reinforced concrete beam.